All right, so good evening once again, students. So from the previous class, we have been looking at factorizing perfect square. We would have gone through the process and the step-by-step process of factorizing perfect square. As well, we had looked at difference of squares. And so today I'm just going to do a quick review of those. And then now we'll see how much practice we can get done before we move on to another topic. All right. So based on what we would have discussed from last class, Ms. Clark, tell me something that you can remember about perfect square. Are you there, Ms. Clark? Because I'm not hearing you.
Yes, sir, I'm here.
Mm-hmm.
All right, sir. With the perfect square, I don't know how to explain it, but the first term and the second term,
All right.
it's
Hold off, Miss Clark. Let me find out. Miss Trivia, you were here last class, right? Miss Trivia?
No, sir.
Okay. All right. Miss Cummings, you were here last class? I'm not hearing anything from you, Miss Cummings. You probably need to try and...
Good evening, sir.
Good evening, Miss Waysome. All right, so I'm trying to get a feedback from what we would have done last time. So as you come in, Miss Waysome, just tell me what you can recall about perfect square from the previous class.
All right, sir. So perfect square, we can identify a perfect square when the coefficient, sorry, of the first and the last term is squared. And also for the middle term again, when we when we multiply the middle term, no, 2 times. Sorry, Miss, come again. Hold on, we are confused myself.
All right, don't bother to come again, Miss Wilson. I have a comment to make. I think you guys are not reviewing, and that's not a good thing. If you're going to tell me something about something, I'm expecting that you start off with at least a definition to tell me what a perfect square is. So remember, in terms of a quadratic expression, there are some quadratic expressions that are referred to as perfect square. And based on the expansion of two binomials, you will find that when you expand to get the product, remember now the quadratic form has x squared at the front and an x variable in the middle and a constant at the end. So in quadratic form, the first term of the quadratic is a perfect square. And the last term also is a perfect square. In other words, the first term is a square term, the last term is a square term, and the middle term would be twice the product of the base of the first and the base of the last. All right, so that's generally the form of perfect square. So let me just refresh your brains. And guys, once again, I'm appealing to you, please be on time, especially for the remaining of these sessions, because I'm going to pick up the pace a little faster. Now that I have some videos there on the topics that we are doing, I'm going to move a little faster. And so this would mean that you would have to become familiarized by watching those videos before you actually come to the class. I'm expecting for you to do that. All right, it is very, very important that is to take that time out just to watch the videos before you come to the class. If you are unable to watch the videos, at least look at the notes and read through it before you come to the class. That's the only way you're going to get the best results from understanding what I'm saying, guys. The moment you come here without any knowledge of what I'm doing, it's going to be harder for you to absorb what I'm saying. All right, so with that said, moving along. So we did look at what a square from a geometric point of view is. We say if we have a square, we have length times length. And if we multiply finding the area, it would be the length times length. So in this case, this square has length x. So we multiply x times x to get the square area. Now, how is the square relating to the quadratic that we are referring to? So if we look at this diagram here, where we have one big square cut up into different parts, and it is cut so that the length of this square, we cut it in two, they cut the length in two parts. One part we label A, the other part we label B, so the entire length would be A plus B. So that would be the same length for all the sides of the big square. But we would have cut up that big square into four parts. And these parts would be cut up so that we have the biggest part would be A square. And the smallest square would be B square. And then now the other two rectangular parts would be AB. Now, this diagram is to portray to you that if you find the area of the big square, which is multiplying the length of AB times AB, you should get the area as it relates to the different parts. So if you add up the area of all of the individual parts, it would be the same as the area when you multiply A plus B times, so A plus B times A plus B, all right? So geometrically, what we're doing can be portrayed with this diagram, but if we are to do it without the diagram in a more abstract way, then we would expand the binomial using the technique that we are familiar with. And so we would multiply distributively, take each term in the first bracket to multiply all the terms in the second bracket in the distributive form. And so we would start out by saying A times A squared, plus A times B, AB. Then we have B times A, which is the same as AB. And then we have B times B, which would give us B squared. And so by doing that multiplication, we would have gotten the product A squared plus 2AB plus B squared. Now, this product here would have been the expanded form of the binomials, right? Now, remember, we started off with this binomial with this square. Then we write it in this form, showing it that it is multiplied by itself. Then we multiply it out, and then we get this form. So this is the expanded form, all right? So what you're required to do, because we are really factorizing the expanded form, you should be familiar with what the expression of the expanded form looks like, and you should have some relationship with the product form, which is the bracketed expression square. So when we have the binomial form, there's a relationship with how we get the terms in the expanded form. And so that we must also become familiar with. All right, so in general, looking at the characteristics, we find that perfect squares, after we expand them, we have what we call the binomial form, which is in the factor form. And then now to the extreme right, we have the expanded form. So if we have a plus b as binomial and we square those, then the expanded form going to be a squared plus 2ab plus b squared. Now, can anybody remind me why we have a 2ab in the middle of the quadratic, the expanded form? Miss Genova, you were here the last class? Miss Cavero, you were here the last class, right?
Yes, sir.
Okay. I have any idea why the middle term is 2ab?
I think because if you factorize it out, you'll get back the same answer as 2a squared plus b squared.
All right. So all right. So I kind of get what you're saying, but apart from just factorizing it, can we see when we expand, when we multiply it out in the form of binomial products? You notice that we would have a times a squared, give it the first term, then a times b, give it what? ab. You agree? So we get a ab here. And now we do b times a. Now b times a and a times b will be the same. So we'd have a plus b times a, which is the same as a times b. And these two terms would be the same what? They would be the same like terms because they have the same letters grouped together and both letters carry the same powers. And when we have like terms, we simply add them. So if you have one AB plus another AB, then you get 2AB. So that's how we get the middle term. Now the last term we get by multiplying b times b, it was b squared. All right, so this is how when we expand a binomial, we always going to get the middle term with twice. We're going to have twice what we have, the AB. In this case, we're always going to have twice a times the b for this form. And if we use any other term in a binomial sense, it's going to have the same appearance. All right. Everybody get that? Let me see if you're following, guys. All right. So Miss Clark, you were about to say something just now. You still want to say what you were going to say?
Sir, I was just going to tell you about how you get the 2AB, but it's all right because I did it already.
Okay. All right. So if you notice here, we have another binomial form, but instead of having a plus sign in it, we have a minus sign. Now, what we would have noticed that this minus sign, the only difference it makes to the final expansion is that the sign of the middle term would take the sign that is in the middle of the binomial, right? And if you look at above, it is the same thing. The sign of the middle term takes the same sign as the binomial. Everybody see that? Other than that, everything else would be similar. So you have the A square, and you have the 2AB, and then you have the B square. Everybody is clear on that, guys? Let me see your hands. All right, good. Now, so what is important about this now? We have to be able to know when we have a perfect square. And in order to do that, we have to look at these properties. And what are the properties we're looking for? In the expanded form, we're going to have the first term as a square term, the last term as a square term. Notice this one, first term is a square term, last term is a square term. Now the middle term going to be 2 times there. If you look at the first term, and I ask you to tell me what the base of the first term is, what would come to your mind? Miss Waysom, what is the base of the first term? Miss Waysom, are you there? All right, Miss Travia, what is the base of the first term? Ms. Cavero, the base of the first term?
A, sir.
Okay. And when we say base of the first term, what we really mean, we mean the base is that which we raise to the power 2. So what we raise to the power 2 here would be the A. So if we're referring to the base, we are talking about either we're just talking about the term without the power. All right. So once I said the base of the first term, you just strip off the power off of it and just give us what the term is without the power. All right. So what is the base of the last term? Miss Cox.
Sir, B.
Right. So the base of the last term is just B. Now, if you look at the middle term, you would notice that you have the product of the bases of the first and last term. So you see you have the base of the first term is A, the base of the last term is B. So the product of those bases would give you AB, and that would always be in the middle. So the product of the 2 bases are always in the middle, and then you would times it by 2. That's always a characteristic of a perfect square. All right, let me see your hands if you understand clearly what I'm saying, guys. All right, so with that said now, then we should easily identify a perfect square in the expanded form when we see it, because those are the things that we're looking for. What about when the perfect square is in the binomial form? What are we expecting? In the binomial form, we must have the 2 terms in brackets, and we're either going to have a plus or a minus sign between them, and we're going to have a square outside the bracket. This here is the binomial form, right? So this is the binomial form, which is also referred to as the factor form, and this is the expanded form. And if you want to call it the product of the binomial, right? All right, so with that said now, we should all be clear on the characteristic feature of a perfect square. Now, once you are able to identify a term as a perfect square, then factorizing it is pretty straightforward, because all we're going to do, and based on this property here, the first term is a square term, the middle term is twice the first term times the last term, and then we have the last term squared. Pretty much what we have been saying about the product or the expanded form. All right. Now, to factorize perfect square, the first step, what we want to do is to check. We want to check the expression if it is a perfect square. So we inspect it to look for all of these properties that we know a perfect square should have. If it have those properties, then we can confirm, yes, we have a perfect square. After we confirm that we have a perfect square, then the factorization would be pretty much a straightforward process, which we'll be looking at shortly, all right? Now, so once it is a perfect square, if it is not written so that the first term is obviously in the square form, then you may need to write those with a number or whatever you have so that they are in the square form. So second step, we write the first term and the last term as squares, mean we write it in the square form if they are not in any square form. And then now, step 3, we would factorize them by just bringing down the bases of the first and last term. By now, everybody should know what we mean by the base. Let me see the hands of those who recall what the base is.
Star A and B.
Right, without the power. So the first and last term without the power, those are the bases that we're referring to. So we say that once we identify our perfect square, we can just bring down those bases in brackets, keep the sign of the middle term, put the square outside, and that would be the process of factorizing perfect squares. Now, that is a short, simple way of factorizing perfect square. But note that perfect square can also be factorized using the what? AC method. Remember, we would have learned the AC method from a previous class, all right? Now, looking back at this example, we would have seen it from the previous class. We're just going to go back to it quickly so that we can get an understanding of what we're doing when we're factorizing. All right, so what we notice here is that we have 9a squared. We have 4b squared as the last term. 9a squared as the first term, 4b squared as the last term. Now, we first need to check those two terms to see if we can write those in square forms. Now, we know that the a is already squared, the b is already squared. So the question is, can we write 9 as a number square? Can we write the 4 as a number square? And if so, we need to just write them in that number square. So what number can we write 9 as in the square form?
3.
We can write it as 3 square. And so we write it as 3 square instead of 9 because we want to establish that the first term is a square term. That's why we're writing this in its square form. So now we put back the a in its square form. Now we're just going to rewrite the middle term as it is. And then now we write the last term in the square form. How can we write the last term in its square form?
2 square.
All right, so we're going to write 2 square for the 4. And then now we write back the b square. Now, in order to kind of simplify how the first term and the last term, instead of just having 3 square a square, we could put the bases in bracket, which is the 3 and the a, put 3 and a in brackets. And then now we put 1 square outside representing the two terms, which is the 3 and the a. So this signifies that they are both squares, right? So writing it this way kind of lessen the codedness by writing 3 squared and a squared. So rewriting the middle term, we get 12ab rewriting now the last term in brackets, we would get 2b all square. All right. Let me see your hands if you are all clear on how we arrive at this point. All right, good. Now, so we would have seen that the first term and the last term can be written in a square form. So that would be indicating to us that what we are working here with